Okay, good afternoon once again. Sorry for that mix-up. I'd lost connection and I'd gone to another meeting instead of this one. So without wasting much more time, I think we're going to start our session for today. And this today we are looking at water conveyance in pipes. Am I audible enough?
Yes.
Yes.
Okay, thank you.
Yes.
Okay, so just again, if I'm too fast, just you can interrupt me if you have any question, so that we move at the same pace. So yesterday we looked at different principles which govern water movement in pipes and in open channels and in any other conduit. So today we are going to focus our attention on pipe flow. So we're going to see how water moves in pipes and how you can use those principles to design an efficient system to deliver water to your farm and to your maybe to your houses at the farm or to the reservoir and any other place where you want to deliver the water. So just an illustration here that water can be delivered through pipes to your fields and maybe for irrigation, and also maybe you might be transferring it from a river. So you use pipes. As you can see here on your top left, there's a pipe being laid in the soil to convey water from a certain place to another place. So this is what we're going to look at and what we need to consider when we are designing a system that needs to deliver water to our premises. So by the end of this lecture or a chapter, because this is one chapter in your module, uh, you should be able to understand the basic concepts that relate to pipe flow. And also, you should be able to design an efficient water conveyance system in terms of knowing, advising on the size of the pipes, and knowing the friction losses, and also selecting the right pumps to use if at all energy will be needed to transfer the water from where it is to your place of interest. So to do this, we're going to look at several principles again that govern the movement of water in pipes. So we'll look at them one by one, and these ones eventually will lead us to us being able to calculate the size of pipes to use, the amount of energy to apply to a system for it to deliver water to our farms at a certain rate, or to have a certain discharge of water at your farm. So the first thing that we're going to look at is the continuity equation. Then we'll look at the conservation of energy principle. Then in the end, we're going to look at energy losses as water is going through a pipe system, how energy is being lost. And this has an implication on how much power you're going to use to deliver this water to your farmland. So we're going to start with the first principle, which is the continuity equation. Basically, what this is saying is that the volume of water that is entering a system for example, that is entering from maybe you're drawing water from the river. The amount of water that is going to enter your system will be equal to the amount of water that is going to be at the outlet of your system. So if you pump 10 cubic meters of water, the amount of water that is going to come out at your farm will be equivalent again to 10 cubic meters. So the mass of the water or the volume of the water will be conserved from the place of input to the place of output. So it's to put it in equation form, we can say that the discharge, which we depict with the Q, at point 1 should be equal to the discharge at point 2. And from yesterday's lecture, we said that the discharge can be found by multiplying the velocity of the water flow by the area of the pipe through which the water is passing through. So at point 1, the velocity multiplied by the area at point 1 should be equal to the velocity multiplied by area at point 2. So what it simply means here is that if you have water moving at a certain velocity, then in your pipe, then at the end of the pipe, you decide to reduce the radius of your pipe or the diameter of your pipe, mean that the pipe has become smaller. It means that on this side of the equation, this A will reduce. And for it to be equal to the left side of the equation, the velocity has to increase. So if I reduce the size of my pipe, it means that water will start moving at a faster rate than it was moving previously. So that's the implication now of having this continuity equation. It will have an implication on the rate, the velocity at which water is moving. If I increase the pipe size, it means that the velocity of water will also reduce. I'm sure you've seen like when you're watering with a hose pipe, water is coming out. Then if you try to push your finger in front of the pipe, water will start moving at a faster rate because effectively you have reduced the size of that pipe where water is coming out from. So effectively, you have reduced the area through which water is passing. And because you've reduced the area, the velocity has to increase so that the discharge from where the water is coming from and the discharge to where the water is coming out from should be the same. So this will have an implication if you have a pipe system, then now you want to maybe increase the rate at which water is coming out at the end, at the outlet. You need to reduce, when you reduce the size of your pipe, water will start moving at a faster rate. But we should bear in mind that as the diameter is reduced, there's also increased friction, and therefore you can't reduce your pipe very much because you incur a lot of cost because there'll be a lot of friction. So effectively now what you want to do is that you want to increase the discharge, but also want to minimize the cost of delivering that water. So this slide is simply what I was talking about, where you have the discharge, the velocity by the area is at point 1 should be equal to the velocity and area at 0.2. So this is just an example to just illustrate what I was talking about. If you have a pipe, this pipe here, it's bigger at one end where the water is coming in from, then it's smaller at the other end where the water is being discharged. So if the area at which the water is coming in is 0.5 meters squared, and the water is moving at a velocity of 1 meter per second, the discharge at the inflow will be the area multiplied by the velocity, meaning that it will be 0.5. But now at the exit here, we've decided to reduce the size of the exit to 0.25 meters squared, meaning that for the discharge at this point, to be equal to the discharge at this point, the velocity at which the water is moving should be increased. So in this case, we have to solve for V2. So this equation now will be set up like this, and we just have to make the velocity subject of the formula. And then when we solve for it, we find that the velocity is 2 meters per second. So you see that now the velocity has increased from 1 meter per second to 2 meters per second because we've reduced the size. So the amount of water coming out of the pipe is going to increase as well. Is it clear? If you have a question, just interrupt me where I'm not clear so that we move together. So that's the
maybe. Hello.
Yes, you can go ahead.
Maybe you come again. Maybe you come again, Doc. But the problem with my internet here. So.
Okay. Yeah. So what we are saying is that water flow in pipes is governed by the continuity equation, which states that the amount of water that enters the pipe is equal to the amount of water that comes out of the pipe, or the discharge that is entering the pipe should be equal to the discharge that is leaving the pipe. Now, if you have a pipe that is bigger at one end and smaller at one end, it means that for the discharge to be equal where there's the bigger pipe and where there's the smaller pipe, it means that at the end where it's smaller, the velocity has to increase so that the water that you have a lot of water coming out at that end because this pipe is smaller. So if we look at the continuity equation itself, it says discharge at one point is equal to the discharge at point 2. And from yesterday, we said that the discharge is a product of the velocity of the water and the area through which it is passing through. So discharge at point 1 will be V times A. Then similarly at point 2, it will be V times A. Now, if the pipe at one end, for example here, it has an area of 0.5 meters squared and a velocity of 1. Okay, so the discharge at this point will be equal to 0.5. So when you multiply A times V, it will be 0.5. Now, as the water is going through the pipe, we decide to reduce the size of the pipe to 0.25. Now, for the discharge to be equal, it means that since the area is reduced, the velocity has to increase. So in this case, if we set up our equation like this, because we want to find now the velocity of the water, we would have to make this V the subject of the formula. And when we solve it, we realize that we have 2 meters per second. So that would be the velocity at the point of, at the outlet. So effectively what we are saying is that for us to be able to deliver water at a faster rate at our farm, we need to play around with the diameter of the pipe. So if we have a bigger diameter, it means that the water will be moving at a slower rate. But if we increase, it means that we'll make it have a higher velocity at our outlet. So effectively, when we're talking about the continuity equation, it has an effect on the diameter, on the diameter of the pipe and the rate at which the water will be delivered. So yeah, so that's the principle there. So as we are designing the pipe systems, we'll be able to look at this as well, how big our pipe should be for us to be able to attain our objective of delivering a certain amount of water. So the main, actually the main objective of this one, this lecture, is for us to design, to know a specific diameter for us to use. So we need to select a right diameter of the pipe. Are people able to get me? Someone has posted that.
Yes.
Or someone is saying that they are not able to see anything on the maybe just by just saying yes, 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 yes. For those who are able to hear me and see the PowerPoint.
Yes, we are able. Not be maybe network where he is.
Ah, okay. Okay. Anyway, since we are recording, we'll be able to send the recording. So we can now move to the second principle. So now we've looked at the diameter of the pipe. One thing which is important for us to set up a conveyance system. But now we are going to look at another principle, which is the conservation of energy. So we know that for water to move, we need to apply a certain amount of force to it, which can be done when we apply power, or we apply a form of energy for the water to start to move. So the conservation of energy principle as well says that the energy in a system will remain the same at every point. It will just change forms. So if I apply a certain energy at the inlet, it will be equal to the energy at the outlet. Only that the different forms of energy will change. So like yesterday, we said that energy, there's potential energy and there's kinetic energy. So if something has a higher potential energy, it will start, if it starts moving, that potential energy starts to reduce while the kinetic energy starts to increase. But in the end, the energy at the 2 points will be equal. So, but today when you're looking at the water flow in pipes, we're going to add another form of energy, which we're going to call the pressure head. So this is the energy that is possessed by the water due to the pressure that is applied to the system. So we have a pressure head due to pressure, the pressure energy, sorry, due to the pressure applied to the system, to the water in the pipe. Then we have another energy, the kinetic energy, which we talked about yesterday, which is due to the water moving. Then the third form of energy is potential energy, or we can call it gravitational energy or elevation energy, which is the energy possessed by water due to its elevation. So if we look at this equation here, it's saying that there are three forms of energy. So this constitutes the pressure energy. Then this, the Z, constitutes the elevation head, which is the potential energy. Then this constitutes the kinetic energy. So at point 1, the energy should be equal to point 2. That's in an ideal system. Here we are using this to show the pressure energy. You remember yesterday we had said that pressure of standing water is equal to the density times the gravity and the height. We remember this one? When we go through yesterday's lecture, we'll be able to see this. So now, because we also said that pressure will be measured in meters. So what we want is to find this H. So we'll make this H the subject of the formula. And then we're going to have this where H in meters will be equal to the pressure divided by the density times gravity, which is this component here. So basically, this is just the H, the height of water in the tank. Then this is the Z, which is the elevation potential, elevation energy. Basically, just it's also just the height at which the tank is from the ground, if we're using the ground as the reference. So if your tank is at 10 meters, this Z becomes 10. If it's at 5 meters, your Z becomes 5. Then also we talked of the velocity of the potential kinetic energy. And you remember yesterday we said that kinetic energy is equals to half mv squared. But now, because we want all these to be in the same unit, we have to convert this kinetic energy to a unit of meters as well. So to do that, we just divide it by this kinetic energy by the mass multiplied by the gravity. So when we do that, this mass will cancel out. And in the end, we are going to have this v squared over 2g. So this g is the gravitational force. So at every point, when we add all this, it should be equal at another point. So for example, in this diagram, we have point 1 here and we have point 2 here. So the energy that the water is going to possess at this point should be equal to the energy that the water is going to possess at that other point. So what will change is that at this point, we can see that the Z, the energy due to elevation is low. Then at point 2, the Z has increased because the water has reached a higher height. But in changing, when Z changes, it means that the other two forms of energy have to change as well. So as the Z has increased, these other ones have to reduce so that the total energy at this point and at this point are equal. So this line will represent the total energy. So we have the Z plus this is equal to a total energy here, which is similar at this point, only that now the Z has increased, but these other components have reduced. So that's the principle of conservation of energy. So we are saying that this is in an ideal ideal system. But in reality, there's always going to be losses. For example, because as the water is moving in a pipe, we talked of friction yesterday. The energy, it's losing energy due to friction. But even if it's losing that energy in the system, we can be able to account for it and then add it to the total. So the total will remain the same, but it's the components that will change. Such that if we look at this illustration here, we are adding two forms of energy. For example, if we add energy to a system using a pump, there's that energy that we are adding using the pump, which I'll call Hg. And then as it goes through the system, due to friction, it will be losing energy. But that energy is not lost out, it's still within the system, but it has just changed from one form, either the pressure, the elevation, or kinetic energy is what now is being converted to this other form of energy, which we are going to call the head loss, which is basically the energy loss. But in the end, the total energy at point 1 will be equal to the total energy at point 2. So this friction loss has an implication on the amount of energy we're going to apply to the system for us to transfer water from the river or the reservoir to our garden or to our field. If we apply less amount of energy, that water will not reach the destination, because by the time it's reaching, for example, halfway, all the energy it had possessed from where it's coming from would have finished, and it will not be able to move to your final destination. So this now has an implication when you're designing your system. So the question now that we can ask is, how do we calculate this loss of energy? How do we know it? So there are various formulas that have been put in place to calculate this head loss, this friction loss. And one thing we should bear in mind, we talked about it yesterday, is that it's the friction of the water and the pipe, the edges of the pipe, which make increase this friction. But also there are other fittings that we apply to the pipes, maybe T-junctions and other things that we put to the pipe. For example, the connectors, the valves, and other things. Those ones, they will increase the friction as well. But the primary one is the surface of the pipe. So if your pipe has a rough surface, it means that you have a lot of friction. But if it has a smooth surface, it means that water will not have a lot of challenges flowing through that pipe. So yeah, like I said, now we have to calculate this head loss in our pipes. Then now, when we calculate this head loss in our pipes, we know that, okay, if we apply a certain amount of energy in our pipes to push the water to our farms, part of that energy will be lost due to friction. So now, if, for example, we are applying a unit of 10 like energy, if the energy we need to pump water from the source to our farm is 10, then we know that, okay, friction is 2. It means that if we apply 10, only 8 will be used to push that water. The other 2 will be lost in the system. So instead of applying 10, it means that we need to increase it maybe to about 12 or 13, so that that 2 which is lost, the rest of the energy will be able to move the water to the point where it's needed. So for us to calculate this head loss, we know that it will be a function of the length of the pipe. So if you have a longer pipe, it means that water has to travel through a longer distance, means that it has to move over a longer surface. It will have a lot of friction before it reaches the outlet. So the longer the pipe, the higher the head loss. Then as well, the higher the water flow, the velocity, if the water is moving at a higher speed, the higher it will lose energy due to friction. This is also related to the diameter. If the diameter is small, it means that water will be scratching through the edges of the pipe, or be rubbing through the edges of the pipe than when you have a bigger diameter. So if your diameter is smaller, you have a higher velocity, and it have an implication on the friction itself. So if you have a smaller diameter, the friction will increase. Then if you have a bigger diameter, the friction will reduce. Similar with the roughness of the pipe, the rougher the pipe, the higher the friction. So from this equation, we can be able to relate those parameters that we've talked about. So this is head loss, which we depict as H with a subscript F, is equals to this F is a friction factor, which is determined by the roughness of the pipe. So the roughness of the pipe, when you buy a pipe, when you go to stores to buy a pipe, they'll give you this value because it depends on how rough the pipe is. Then this is the length of the pipe. So now you start to design yourself. If you have a longer pipe, you know that you're going to encounter. Now it will increase the friction. Then if you are moving water at a higher velocity as well, if you increase the velocity, this value will also increase. But when you come here to the denominator where there's the diameter, if you reduce the diameter, it means that this will increase. If you increase the diameter, it means that this will reduce. So when we're designing, we need to now look at this formula. But in reality, what we are saying is that the head loss can also be calculated based on the height difference of the 2 points. If we look at this diagram here in this figure, it shows that there's a reservoir here, and it's delivering water to a second point here, which is maybe a tank at your farm, from which now you'll be able to water your plants. So using these two points, there at 1 and here at 2, we can be able to determine the head loss based on the height of these two. So I said we can use that equation, the one that I've shown previously, but also we can use the continuity equation on its own to determine the head loss. How we can do that? We know that energy possessed at this point, at point 1, should be equal to the energy possessed at point 2. Okay? So if here at point 1, we can start separating the forms of energy at this point, then also we separate them at this point. What we realize is that at point 1, because like yesterday we said that the pressure at one point is equal to the force over the area. And we said that water in a tank, in a standing tank, at the bottom of the tank, the pressure will be equal to the weight of the water that is pressing on the surface. But if I put my point at the top of this water reservoir, it means that.
Sir, sorry, I don't know if it is me alone. The slide is still on calculating head loss. The slide is static with me. I don't know if it's my network alone or it's. Thank you.
Okay.
Maybe it's your network, because us, we are on water flow in pipes.
Yeah, we are
on head loss using continuity equation.
Yeah, where there's a diagram.
That's where we are.
Yeah, that's where we are actually.
Okay, maybe it's my network. Thank you.
Okay, all right. So at point 1, can someone be able to tell me what the pressure will be here at point 1? Just a quick guess, if anyone can remember what we talked about yesterday.
30 meters.
It will be
30 meters.
Okay. So remember, we said that if we have water, like for example in here, at the base here, the pressure will be equal to the height of the water. Okay. So if my point 1 was here at the base, then it will be 30 meters, sorry. But if I am at the top here, at the top of the water here, on top here, it's open to the atmosphere. Just it's air, basically. So it means that my pressure here on top would be, anyone?
0.
Yes, 0. So because here there's nothing pressing against the water on top, so my pressure here will be 0. Okay. Then at this same point, because this is the reservoir. At this same point, so I've said that my pressure is 0. Then my velocity, because this is a reservoir, water is not moving at this point. So I expect my velocity, my kinetic energy as well to be 0 at that point. But the potential energy will be equal now to the height of the water. So from a reference point, for example, if our reference point is here or anywhere, so the energy here will be equal to the number of meters from here to where our reference is. For example, if our reference is here. So at point 1, this energy will be 0. This energy will be 0. And of course, we're not applying any, we don't have any pump there. So this as well will be 0. So the only source energy component that we have is Z1 at this point. So this the energy here, which is Z1, should be equal to the energy at this point. And again, if we come to this point, our pressure will be 0 because we are at the top of the tank here, and it's open to the atmosphere. So this will be 0. As well, the velocity will be equal to 0, such that now the only two components that we have will be the elevation and the head loss, which was experienced in this pipe. So the energy here, the energy here will be equal to the elevation here plus the head loss. So when we do that, here I'm just showing the components which are 0. And in the end, this is what we're talking about. And actually now, the head loss will be equivalent to the height difference from here to here. So in this case, the height difference is 30. So this will represent our head loss as the water moves from this point to this point. So if you're given, if you go in the field and you have where you're drawing your water, maybe it's at 5 meters, and then where you're taking your water, maybe it's at 2 meters. For example, if you are using a certain reference, a reference can be anything. It can be sea level, it can be any point that you pick. So you're saying, okay, this water is at a height of 5 meters above a certain reference. So if you're moving your water from a place which is 5 meters above to a place that is 2 meters above, we are saying that the head loss there will be 3 meters. That's one way. Another way of calculating the head loss in reality. So we're going to look at, we're going to use this as well to determine the diameter of our pipe. So we have two things here which we need to know, that we need to know the diameter of the pipe to use, and we need to know how much energy is being lost in that pipe. So if you look at this, the previous equation in the previous slide, we are saying that as we reduce the diameter, the head loss is increasing. And so, of course, if we reduce the diameter, we increase the rate at which the water is coming to our farm. But it's at the expense of losing head. So meaning that you have to pay more money to buy electricity units for you to pump through smaller pipes than when you have bigger pipes. So those two things are the ones we're going to consider when we now want to come up with a final decision of what diameter of the pipe we need. So before we proceed, we'll look at ways in which we can reduce these head losses in our pipe system. So one of them is, of course, using pipes with a larger diameter, but that will mean that you spend a lot of time in pumping the water because you have a lesser, the water will be moving at a slower rate in a bigger pipe. But also the second thing that you can do is to minimize on the bends, minimize on the T-junctions, so such that when you're designing a system, make sure maybe you just put the main pipe in the middle so that the branches which go to different sections of the farm are minimized, rather than if you put it on one, on maybe the far end of your field, it means that you have to put a lot of corners for the water to reach your destination. So what you need to do as you are designing, make sure that you minimize on the bends on the pipe. Make sure that you have one straight main line where smaller ones will connect going to your fields. But the other thing is that you can use pipes which are smoother, in the internal surface, and that will make water to flow smoothly. So those three can help you reduce the head loss. Now we've come to the point now where we need to design. We need to come up with the size of the pipe to use to deliver water to our field. Bear in mind, we will always know that, okay, we need this amount of water in our field. So in short, we are saying that we will know that, okay, we need this volume of water to be delivered to our field. And that volume of water, we can calculate it, and we know from our previous lecture that is just basically the discharge, which is the volume of water reaching our farm in a unit time. So we know that, okay, we need 1,000 cubic meters of water reaching our farm in this number of minutes, okay, for us to irrigate the whole area. Then knowing that, now we need to find, okay, what diameter of pipe can I use for me to achieve that that volume of water reaching my farm. So we know from the formula of discharge that discharge will be equal to the velocity multiplied by the area. Okay, so using the area, we are able to find the diameter, because area will be equal to d squared pi d squared over 4. So this is coming from the formula that we saw yesterday, where we said area is equal to pi r squared. I'm sure we remember that, pi r squared. So the r in that formula is the radius, and the radius is half of the diameter. So if we replace the radius by diameter, it means that we are saying diameter divided by 2. And because that r was squared, if we square that diameter divided by 2, it's going to be diameter squared divided by 4 this time, because the 2 as well will be squared. So this is where this formula is coming from. So what we can do here, where there's A, we can replace it with this, such that now in our formula, we're going to have the diameter of the pipe. And if we have that now, we can see that in this equation now, the only thing that we know is the discharge. We don't know the velocity, and we don't know the diameter. But now, because we had this other equation as well for head loss, which has those two parameters, velocity and diameter, we can now solve these equations simultaneously. I'm sure back then in high school we did those. We solved those equations, simultaneous equations. So now in this In this course now, we're going to apply that principle that we use in mathematics. I don't know if it's in mathematics 10 or 11 or 12. So we have D and V unknown. Even in this side, we have D and V unknown. So what you can do is that from this equation of discharge, you can simply make V the subject of the formula, which is the velocity. And when you make it the subject of the formula, you just replace it here. And once you do that, the only unknown in your equation will be your diameter. And then now you can solve this equation for D. And in that case now, you would have accounted for your head loss while calculating your diameter. So at the end of this, the next slide, we're going to see an example of just what I was talking about, just to see how it flows. So when you do that, it means that now you're able to come up with a correct size of your pipe, the correct diameter of your pipe, and now you can recommend to say, okay, for this farm, for us to move water from a location which is, for example, 100 meters, we need a diameter that is at least this size for us to be able to deliver water to this farm at such a rate. So basically, that's what we want to achieve in this chapter. For you to be able to advise to say, okay, use this pipe size to deliver this amount of water if you are going to deliver water from a certain distance. Okay. So before we go, we illustrate using an example of how we can be able to design a pipe size. I just want us to go through this last slide about pumps. When you go to your module, you find that there's a lot more about pumps, so you can just read through. So basically, to just be talking about different types of pumps. But here, the principle which I just want to show you is that pumps are important because most of the time, if we are pumping water, it will be from a river. And in most cases, the river will be slightly below the elevation of your farm. So the river will be lower, at a lower elevation, then your farm will be at a higher elevation. So if you put a pipe to transfer water from your river to your farm, water will not go because it has to overcome that height for it to move to your farm. So basically what we do is that we install a pump which is going to suck water and then deliver it above there to your farm. So for you to do that, you need to apply a certain form of energy. And that energy is what we've been talking about, like if you apply an energy in a pipe to push water to a certain destination. So if we apply a certain energy for water to move from here to here, we should know that there's also friction in this pipe, which is making you to lose some of that energy. So you need to apply a higher amount of energy to move water from here to here and also account for the energy that is being lost by friction. So here's just, these are just examples of when you would need to use a pump. It's not always that you need to use a pump. So if your reservoir is at a higher elevation than your field, it means that you're just going to use the natural energy to move your water from the reservoir to your farm. But if your farm is at a higher elevation, now you need to add a pump your water to that elevation. Is it clear before we go to the calculation, the one that I want us to go through this, what we're talking about, but using an example? Or it will become clear as we go through the example, I think. Okay, so I'll stop sharing this screen. Then we'll go to this example. So this example is in your module. So in your module, you've just been given this question, but the solution is not there. So this one is what you need to do in that question. So you've just been given the question and the answer. Then they want you to go through the procedure of finding that answer. So we'll just go through it, and then if you have any questions, we can you can interrupt me so that we move together. So they are saying we have a 2.5 kilometer pipe that connects a reservoir to a small storage tank outside a town, which supplies water to individual houses. So you have a reservoir, which is 2.5 kilometers away. Then there's a pipe which is connected to it, which is delivering water to another small tank where people in the neighborhood are able to draw water from. Then now they are asking us, determine the pipe diameter when the discharge required between the reservoir and the tank is 0.35 meters squared per second. So this discharge has been determined based on the usage of the water. We know that if we deliver this amount of water per second, it will be enough for all the families to draw a certain amount of water from that tank. So that's how come this was derived. And they're telling us that the difference in water levels between the reservoir and where the tank is 30 meters. Okay, and we are assuming that this this factor in our equation, we called it the F. It was the F, the friction factor is 0.03. Now, for us to solve this problem, if we look at this equation down here, we see that that's where we have diameter of which we want to calculate, but we don't have information on the head loss. We have not been given any information on the head loss, but we can actually do that, like we said in those slides, using the continuity equation. So the diagram for this problem is the one that I showed you previously in the slide. So we said that, let me just show it here. So it's basically this, the same slide. So we said the pressure here will be 0 and the velocity will be 0. The only thing which will be affecting the energy here will be the elevation. Similarly to this point, the pressure will be 0 and the velocity will be 0. So the energy here will be equal to the height and the energy loss in the pipe. So if we look at this equation again, this will be 0, this will be 0. The only thing which will be there will be this one, Z. At point 2 as well, this will be 0, this will be 0, and you only have these two parameters. So if we cancel out these ones which are 0, the equation will become like this, where the head loss will be equal to basically just the height difference. So in this case, our height difference will be 30 meters. So now we have calculated this one, and if we look at this equation, this we have, the diameter. The diameter is what we are looking for. The velocity we do not have. So we have two unknowns. So this velocity, the velocity we can determine it using the formula for discharge. We know that discharge is equals to the velocity times the area. And for the area, just move down. For the area, we said area will be equal to d squared over 4. So this is coming from pi, where we said from the yesterday's lecture that area will be equal to pi r squared. And r is simply the radius, which is half of the diameter. So if we are to use diameter, it means that we have to divide it by 2. But because we are squaring it, this 2 below becomes 4, because 2 squared will be 4. So this will be the formula for the area. And so we are still using this equation. So this velocity is unknown, and that's the one we want to replace in that equation. So from the formula where we said discharge is equals to velocity times area, we can now replace, where there was area, we replace it with this value. And when we do that, you're going to find that your velocity will be equal to 4 times the discharge divided by pi, the diameter squared. And now we can be able to calculate the velocity because we have this discharge, which is in the question, which is 0.35. So when we solve for this, we see that velocity will be equal to 0.446 divided by the diameter. Okay. So in the head loss equation now, where there's velocity, we can simply replace it by this value. And when we do that, so the whole lot of this, we can add it here where there's v here. So when we do that, it means that the only thing which will be missing in our equation will be the d, which is the diameter. And it means that we have accounted for our head loss. Now we just want to find the actual diameter. So when we put this in the equation, you come up with this, you end up with this, such that now your d is the diameter is the only unknown parameter in your equation. And when we solve for diameter, because when we multiply this d and this d to the power 4, it will become d to the power 5. And such, you can just take the 5th root of the diameter of d, and we're going to end up with a diameter of 0.47 meters. But we know that for pipes, the diameter is just measured in millimeters. So in the end, you're going to have 470 millimeters 470 millimeter pipe. So for you to deliver water from that reservoir to that tank at that discharge, you should have a pipe that is 470 millimeters. If this value is a decimal, you move to the nearest whole number. So maybe if again you find that the pipes being sold, they are moving in units of 10 or maybe in units of 50, you find that the nearest pipe to this would be a 500 millimeter pipe. So that's the pipe that you would use now to deliver water to your farm or to those houses at that discharge rate. So it's similar. If you are supplying water to your farm, you know that the amount of water that you need is this amount, which is basically the discharge. So now you design a pipe size which is equivalent, which is going to deliver that amount of water to your farm. So this is basically how we go through the process of getting the diameter of a pipe. So I'll be able to post this in the WhatsApp group. Just this this problem that we have gone through, but also I'm going to add other problems, different situations, so that you're able to go through and see how you can solve these problems. So maybe by the end of today or tomorrow morning, I'll put problems or questions that from chapter 1 for yesterday and others for chapter 2 for today, so that you just have a feel of how to use these principles. So I wish to end there, unless there are any questions.
Thank you, Doc.
Okay. Yeah. So if I'll send this this PDF document for you to go through, and if you have any problems anywhere, tomorrow before we start tomorrow's lecture, maybe you can ask where you have problems, then we can go through. Okay, so if there are no questions, we're going to end here today, and tomorrow we'll now look at the movement of water in open channels. Okay, so I'll end here, and we'll meet again tomorrow.
Thank you.
Thank you.
All right, welcome.